So today, we're going to continue our discussion on the concept of energy. So let me just review what we did last week. We talked about the work kinetic energy theorem. All right? And what that says is that the work, which is defined as the integral, is equal to the change in the kinetic energy, which is 1/2, let's say, the final squared. So if the force is constant, then this just becomes where this is the change in position or the displacement vector. So in today's quiz, all you had to do was write this equals that and solve for the cosine of the angle, which for today was that. All right, so the direction is given by the cosine of theta. And you had to indicate on your diagram what theta meant. All right, you were given F, and you were given D. And you were given this, and you were given that. All right, now, under certain circumstances, the work done by a force only depends on the starting position and the ending position. It doesn't matter how you got from one place to the other. All right, now an example of that, in fact, the only one we know right now, is gravity. All right, so let's take a look at that. Let's look at the work done by gravity. So let's say I take a path from here to here, and this distance we'll call y, right? So the force is this way, and that's equal to mg. Okay, g is downwards. And if we call this the 1 position and this 2, okay, so what is the work done in going from 1 to 2? What would that be? Say y is a positive number, and we're going from here to here. What is the work done? So what would it be? Minus mgy. Very good. Anybody object to that? Now we're going to do a similar situation. Gravity is going, the particle is being lifted up to here and then brought to here. And then it goes over here and back to there. So this is the path taken. This is still y. This is 1, this is 2, and these are other points. All right? What is the work done in going by gravity and going like that? So I'm going like that, all the way around like that. Looks complicated. It's the same. So the work done here is still, all right? So why is that? Well, first of all, the work going from here to here due to gravity. This is due to gravity. The work done from here to here is 0. Why is the work done from going from here to here 0? And I'm moving. I'm going from here to here. I'm carrying the ball from here to here, then here to here, this section. Yeah, so why is the work done in going from here to here 0? The height is not changing. So why is that relevant? So the important point is that the force is perpendicular to the direction of motion. And by this rule here, the cosine of 90 degrees is 0. Okay? So there's no work done going from here to here. In this part, it's not as clear, not as obvious, but when we integrate along this curve, we're going to get a negative integral going up, and then when it comes down, we'll get a positive integral that'll exactly cancel. It'll cancel because the force of gravity only depends on y, right? So if I integrate from here to here, okay, the change in y is 0. So because the change in y is 0, there's no work done due to gravity in going from here to here. Okay? So a force where the work done does not depend on the path, but only on the beginning point and the ending point, is called a conservative force. So the work does not depend on the path, but only on the change in position. So this means we can define a function that indicates that change in position, that change in work, that work done. So that implies we can define a function. And the way we define it is the following to R2 F dot dr. So the change in this function is equal to minus the work done by that force. And because of this, we can give this a name. These functions are called the potential energy of the system. All right, so U and R is equal to the potential energy associated with the force F. All right, so we have a force F, and we have a potential energy that goes with it. The result of this is that we can rewrite the work kinetic energy theorem as delta U minus equals delta K. The change in potential energy is equal to change in energy, kinetic energy, if the force is conservative. And if there's more than one conservative force, we can write it as the sum over all of them is equal to delta K. So if there's more than one conservative force, and we'll discuss one other one today, we have this thing, and now I can write it in another way. I can write this as the U I at R, let's say 1 plus K1 sum over R is equal to, okay. So what I've done is I've replaced the deltas with the actual quantities. So we have the potential energy at R1 for all the forces. We sum them up. Is it plus the kinetic energy when the particle is there is equal to the potential energy at R2 plus the kinetic energy at the second location. All right? So we have this result. And this statement is getting us to something called the conservation of energy. We have the conservation of energy there. So far, all I've done is rewritten Newton's second law. So this particular form of the conservation of energy is only accurate when I have only conservative forces. So I have only potential energies involved. But it turns out the conservation of energy is more general than that. And what I could do is I can add to this side of the equation other forms of energy and also to this side. So if I lose energy due to friction, I can add that energy into that equation. If I lose energy due to sound, I can add that in there. If I lose energy or gain energy due to light, I can add that into that equation. So this equation plus other forms of energy can be used. Does that work? What it means is that the amount of energy at one location at one time is the same at a different time. In order to do that, to use that, you have to define your system. You have to define the system that you're talking about. All right? This is pretty abstract, and we'll make it more concrete in a minute. So the conservation of energy is even more important than Newton's second law. If you do advanced physics, usually use energy concepts rather than force concepts. So there's two things I need to tell you in order for you to actually use this. All right, so the first thing I want to do is list some properties of potential energy. All right, so let's do that. And then I'll say a few more words about conservation of energy, how to use conservation. Just things to know about potential energy. Number one, potential energy is a function of position. All right, so that's one thing. Secondly, and it does not depend on, the changes in potential energy do not depend on the path taken. All right, the second is the only differences in U have physical significance. So what does that mean? I have to define my zero of potential energy. I have to define where the potential energy is zero. So typically, if we're doing gravity, gravitational potential energy, I might define the floor as zero. So the potential energy is zero at the floor. But if I'm dropping something on this desk here, I might want to define this desk to be the zero of potential energy. So it's completely arbitrary where the zero is. It's no different than defining position. You have to give a reference point, an origin. So the same thing is true here. We have to define a zero. So we must define where U of R equals 0. All right? And that's totally up to you. Of course, there are good choices and there are bad choices. Good choices are to choose places where the particle has a zero, is at. So if the particle is at a location, it's frequently good to choose that location to be 0 and then look at other locations to be non-zero. Third thing, what is the unit? So potential energy is energy. Energy unit is called a joule, which equals a Newton times a meter. So a Newton meter is a joule. That's the MKS unit of energy. And probably most importantly, not all forces have a potential energy. All right? Can somebody give me an example? What's a force that has no potential energy associated with it? Friction. All right? Friction has no potential energy associated. Why? Because the path matters. All right? If I move my computer back and forth, all right, I've lost some energy to friction. There's no potential energy associated with where this computer is. There's no frictional potential energy. What about the normal force? Does that have a potential energy associated with it? No. No. It doesn't even have any particular value. It's just determined by other forces. What about tension? The answer to that is a little more subtle. Depends on how we model a rope or a string. If we can model it such that the string or rope can change its size, right? Like we can stretch it, okay? Then we can model it as a spring-like force, in which case there is a potential energy associated with it. So what I'm going to do is I want to introduce one other force that we haven't used much yet. So this is the spring force. Everybody know what a spring is? Something you can compress or extend. I'll just write the one-dimensional example. All right. So this is, you can think of this as like a spring. And if I had a mass at the end of it, then if I compress the mass, if I move it this way, the spring force will be that way. If I extend the mass, the spring force will be back. So that's why we have a minus sign over here. All right? That minus sign tells you that the spring force is opposite to the way the object is compressed or extended. The potential energy associated with this oops, I left something out. Anyone notice what I left out? I left out the spring constant. So this is called the spring constant. You should be paying more attention. There we go. So that's the potential energy associated with this force. How do I get this? I just integrate. And remember, the integral of x is x squared over 2. So I have a square over 2. The minus sign goes away because the potential energy is defined as minus the integral. Okay, so that's why there's no minus sign in there. In principle, I could define somewhere else to be the zero of potential energy, but it's most convenient to find the zero to be where the spring is unstretched. This is called the equilibrium position, where it's unstretched, uncompressed, not compressed, not stressed. All right, so that's the equilibrium position. So what we want to do is learn how to use conservation of energy. Turns out that in many, many problems, energy is so nice to use. So much better than forces. One good reason why energy is useful, easier to use, is because energy is a scalar, not a vector. And that makes life a lot easier. We just have to calculate things as numbers. We don't have to worry about direction or components of vector forces. Right? So that's one thing that makes energy much more useful. Okay? So how do we use it? As with every single problem you do, the first step, what do you think the first step is? Any problem I give you so far, what is the first step? Draw a picture, that's it. All right, so you want to draw a picture. So the importance of this, in particular, to define your system. The idea of conservation of energy is the energy going into the system must equal the energy coming out. Or if you have an isolated system, the energy is constant, okay, within that system. Let me ask you the following question. All right, I'm going to drop this whatever it is, scissors. I'm dropping it. And I want to use conservation of energy to figure out, let's say its speed at the bottom. So I drop it. All right? So the question is, what is the system? Is the system just the scissors? What are the energies involved? Gravity. Anything else? What other kind of energy? Kinetic energy. All right? So we have gravity and the kinetic energy. Already, we're in a somewhat subtle issue over here. Because what is causing gravity for that scissors? The Earth. So is the Earth part of the system? Yes. All right, so I have the Earth and the scissors together is my system. The potential energy change is due to the Earth. And I have to worry about the kinetic energy change of the scissors. But what about the kinetic energy change of the Earth? Why don't I worry about that? Mass. What about the mass? It's too big. So what does that mean about its kinetic energy? Seems like it would be big. Change in the kinetic energy is essentially zero. All right? I mean, there are more subtle ways you can think about it. You can think of the Earth as your reference frame, and we're only interested, so everything is relative to the Earth. So in which case, the Earth's always zero, right? Relative to the Earth, the motion of the Earth is zero. Okay. All right. So we have to keep track of what our system is. And when we're dealing with gravity, we have to include the Earth, but we don't have to include its kinetic energy. All right. The second thing is you identify important positions. So these are positions where you either know something or you want to know something. So for the scissors, the important positions are here and the ground. Right? Those are the important positions. I don't need to know anything in between. Right? It's only the top and the bottom. Now, in some cases, there may be more than two important positions. So you identify those important positions. The third step is determine all the values, let's put it this way, determine the values of all forms of energy at each important position. So I determine the kinetic energy. I determine the potential energy. If there's more than one kind of potential energy, I determine the potential energy for each kind. And I do that at each position. In addition, if there's energy lost or gained, I have to indicate that. So if friction or something else has added or subtracted energy, I have to consider that as well. The fourth thing is we set the total energy at one position equal to the total energy at another. All right? So you do that. After that, it's just algebra to calculate what you want. All right? So this is pretty abstract, so let's do an example. So I like to use examples from movies. All right? So this is a typical situation in almost every action film you've ever seen. Somebody jumps out of a window, lands in a trash bin, and survives, right? How does that work? All right, so we're going to model that. So we have a person up here, and that person jumps or falls down here. We'll call this distance h. Okay? And then there's some object there that's elastic. Right? And we're going to model that object as a spring. Right? So we're going to model it with a spring with a certain spring constant k. And our question is, how big is this? Okay, that's going to be our question. All right, so we have to know something about k, the spring constant. More typically, maybe you know d, how much it's compressed, and you can compute the effective spring constant. Either way, we have a nice problem. Now remember, whenever you put in information, unless something is 0, it's better to leave it as a symbol, because then something might cancel out in the end. All right, so let's figure this out. Now, I want to identify the important positions. Where are they? Name one. Starting point. Good. All right, so there's one position. All right, I'm going to ask you a few questions about that position. What's the kinetic energy at that position? 0. So I can write K1 equals 0. What's the gravitational potential energy at that point? mgh. All right, now when you said that, you assumed that this point is 0, right? All right, so this is 1g, gravity. What's the spring potential energy at that point? All right, why is that? Why is it 0? Nothing's happening to the spring. Good. All right, pick another position. Just like he picked up here, you pick another position. See that? The middle one. Is that what you said? Where do you want to choose? You want to choose this point? Yes? All right. So we'll choose that point. All right. What is K2 there? What do we know? Do we know anything there? Is it non-zero? Yes or no? Yes, it's non-zero. It's not 0. All right, so we don't know. We'll just write it out, what it equals. So we might need to know the mass of the person to do this problem. So let's give that person a mass. All right, we might need that. All right, what about its gravitational potential energy? What do you think that is? 0. All right, so that's 0. What about the spring potential energy? What do you think that is? So it's 0. 0. Why is it 0? It's not yet compressed. Okay. All right, there's only one other important point left. So that's this point here, right? All right. What is K3? So the person lands, and this is as far as it goes. So what do you think K3 is? The kinetic energy at that point. Not 0. Are you sure of that? That's as far as that person goes. So you're going to compress the spring and then that's it. So you're not moving at the bottom. When in these action films, somebody jumps into what do they jump into? A trash container. They jump in, they compress down the trash, and then they come to a stop. So what does that mean the kinetic energy is? All right, so we get 0. Okay? All right, what about the gravitational potential energy? That's good. A lot of times people forget that. but that's good. All right, and what about the spring potential energy? What is that equal to? All right, so what is the spring potential energy equal to? What do you think? 1/2 K d squared. Okay, so that's it. All right, so we have all those. Now we can do various things. So part 4 over there, I could say the energy at 1 equals the energy at 2. So that implies mgh equals 1/2 mv2 squared. And that's it. So I can calculate V2 if I want. I could also say E1 equals E3. And that implies mgh equals mgd. All right, 1/2 kd squared. OK? So here perhaps could solve for something. OK, it depends on what I know. And then I also have E2 equals E3. So that implies 1/2 2 squared. That's all there is to it. OK, so you use this strategy. These problems are trivial, but you have to use the strategy in order to do it. You draw a picture. You identify important points on the picture. You find all the energies at that point. You determine the values of those. And then you set the total energy at one place equal to the total energy. Now, what if I said to you, while it was going through the air, there was friction, and it lost an amount of energy. I'll call it E DIS for dissipated. So a certain amount of energy lost from the system, E dissipated. This is a positive quantity, but it's lost to the system. How would I change that here? Over here, what would I do to any of these? What would I do? I lost this energy. All right, so this is the energy lost from here to here. How would I add that in? How would I deal with that? Where do I put that? In here, here, or here. So if I do this, notice what happens. Now, EDIS is a positive number, right? And you're subtracting it, right? When I solve for V2, is V2 bigger than it was or smaller? It should be smaller, right? But what is it according to this? Solve for V2, I put this over to this side of the equation. Do I get a bigger number or a smaller? Bigger. So this minus sign, it should be plus. That's how you figure it out. You use physics, physical intuition. All right, what about this equation? Same thing? What about this equation? You don't do anything here because this deals with going from here to here, and there's no change in energy due to friction. We said that EDIS was due to friction. Okay? This is all there is to this kind of problem, okay, using conservation of energy. So there's one more topic. I don't think this topic is discussed in the textbook, but it's important, particularly useful in chemistry and some other areas. All right, and that's the use of energy diagrams. All right, I'm going to draw a potential energy as a function of x. And this might look something like the following. All right. So that's the potential energy diagram. think of it like a bunch of hills and valleys. All right? And there's a total energy for the system. And I'm going to draw that total energy right like this. So that's the total energy. If that's the total energy, question is, where can the particle be? This is the potential energy. This is the total energy. Where can the particle be? The only energy that's not shown on this diagram is what? The kinetic energy. The kinetic energy is positive, right? So if I'm located over here, my potential energy is bigger than the total energy. If I add in the kinetic energy, I'm still bigger than the total energy. So I can't be there. I can't be above this line. The only place I can be is here and here. Those are the only locations I can be. And what happens if I am there? Supposing I start out right here. So I start out at this position. Okay, so this is my potential energy. Do I have any kinetic energy? Yes. Why? How do you know that? Because the total energy is greater than the potential energy. So the difference between those two is the kinetic energy. What's going to happen if the particle is over there? What's its motion going to be like? Just going to sit there? It's going to move? Which way? Is it going to move this way or this way, towards positive x or negative x? All we know is it has a kinetic energy. We don't know which direction. It can actually go either direction. When it goes this direction, what's going to happen to it? If it goes this direction, the particle will move up. Its potential energy will increase. What does that mean about its kinetic energy? Decrease. It's going to decrease until the kinetic energy is 0. That'll be at this point where the potential energy equals the total energy. Then what's going to happen? What do you think is going to happen then? Is it going to just sit here? It's going to slide down. So it's going to go down. What's going to happen? Is it going to stop anywhere? No, it'll keep going until it gets to this point. And then it'll oscillate back and forth, back and forth. You can see perhaps why this is so important. Because we have so many situations in physics where we have oscillatory motion, particles going back and forth. And they do it because we have energy diagrams like this. Let's put a new, let's say the total energy was like this. All right, let's see what happens there. All right, let's say we started out at this point, and it was moving in that direction. The particle is going to go up here. It still has a lot of kinetic energy, so it's going to go over there. It's going to actually go over the bump here. It's going to come down here. It's going to go up here. And that's as far as it can go. It can't go over there. So it'll come back here and like this. All right, so it goes back and forth like this. Okay? So that's how the particle will move. So the way to read these diagrams is to imagine a bunch of hills and valleys and like a little marble that's going down. You know what a marble is? Anyone know what a marble is? A little ball moving back and forth, back and forth. It's rolling down, where we ignore the rotational motion. Okay? So that's how these things work. If a particle is sitting here, it's called stable equilibrium, because the particle can oscillate back and forth here. If the particle happens to be up here, let's say the total energy was like that, this is called an unstable equilibrium. because if the particle moves just slightly to the left or right, it falls down. Okay? It doesn't oscillate back and forth. So that's where the concepts of stable and unstable equilibrium. Okay, I think we're all done.